So we are going to talk about our next lab, which is lab 2. Now in this lab we learn about multiplication, addition and decimal adjust. Okay, so we already have talked about a lot of instructions, and we tried in quizzes, and we also modified the code in lab 1. Now in this lab we will learn some new addition exceptions, and also how to resolve those issues. So let me show you an example here. So let's say to understand what we are doing in the lab 2, let me show you here. So for an example, let's say you have two numbers which are BCD numbers. If you recall the BCD numbers are binary coded decimal numbers that you have learned in digital circuit class. So these numbers are actually decimal numbers, but these are written in a different number system. For an example here, as you can see, for an example, we wrote like 2, 3, 1, 2, 5, 6. So just by looking at the number, you probably don't know whether this is decimal or a hex, right? Because all these digits belong to decimal and also belong to hex. But let's say if I tell that these are decimal numbers, so that means you are actually doing the decimal addition. Okay? Now, to do this addition, what you need to know? You actually need to know a couple of things. Number one, you need to know how to do multiplication addition to add large numbers. Now what do I mean by large numbers? If you look at the numbers, each of the numbers has like 6 digits, right? Now even if I'm telling the numbers are decimal, but when you will add these, your microprocessor will treat this number as hex. So that means every digit here in hex will have at least 4 bits in binary. So basically this is going to be a very long byte, right? Like 3 bytes. You know what I'm saying? Now, the registers that you have, which you used to add like accumulator A or accumulator B, we just have those for 1 byte each. But we need to know how to add two numbers where each number is 3 bytes long. So this is called multiplication addition, when you add large numbers which are more than 1 byte. So we'll talk about this in this lecture. We also want to know how these microprocessors handle the addition of binary coded decimal numbers. Because the microprocessor actually cannot add binary coded decimal numbers, because every time you're trying to add the binary coded decimal numbers like BCD numbers, those numbers are treated as hex. So even if you don't want hex addition, your microprocessor will actually add the numbers as hex. Now we need to know how we can adjust this, okay? And at the very end, we also want to display the answer, okay, from the memory map. So in the quizzes, you have seen how the memory map look like. We have been, using the map in many quizzes, but the map is actually there in our Fox trainer board. Memories. So every time you do something is changed in the map, and data are changed. But also, so we will see today how you can actually check the map and see what data you have there. Okay, now let's first try to understand how we do the multiplication addition, meaning how we add numbers which are more than 1 byte long, because you cannot add the more than 1 byte long number addition at once. You have to actually do it in several steps. Now for an example, to make it simple, we are using 2 different numbers here. The first number that we have is 17A3. Now, again, remember, at this point, we are just trying to understand how you add 2 numbers where each number is more than 1 byte long. So we don't care whether the numbers are BCD or not. Look at this, the numbers are not BCD, because BCD numbers are the decimal numbers, right? Now you should not have A there, because A does not belong to decimal number system, right? So we are just trying to show you first how you add two numbers which are more than 1 byte long each. Okay? So don't think that these are BCD numbers. These are just regular hex numbers at this point. Okay? Now, again, we all know that we have accumulators to handle the additions. So we have accumulator A and accumulator B, and both of those are 1 byte each. But the numbers that you have at here, both of those are 2 byte each, 2 byte long, right? Again, how do you add this? We can add the lower byte first in the first step, and then we can add the higher byte, right? Does it sound better? Now, for an example, if you look at the lower bytes, in the first number, the lower byte is A3, right? In the second number, the lower byte is B9. So what we can do is we can add this lower byte first, and then we can consecutively add the higher bytes, right? For an example, once we are done with the lower bytes, then we can again go to the number and then add the higher byte. Like the first number, the higher byte is 17, right? In the second number, the higher byte is C3, so you can add C3 and 17 in the next step. All right, so does it sound good? Do you think this is all right? I'm saying it would work. There is a little catch here. Now, let me show you what is the problem. The problem is a carry, because what can happen is when you are adding the lower bytes, for an example here, let's say you are adding the lower bytes, let's say you are adding A3 and B9 at the first step. Now it's possible that you might have a carry at the end of that addition, which should be propagated to the next level as a carry. So here you see, when we added A plus B, we have a carry which needs to go to the next column, right?
Yes.
Now that makes this complicated, because you cannot add the lower bytes and the higher bytes separately. That's the complicated part, because even if you are adding the lower byte, then you might run into a carry which you need to add in the next step. Okay, like this one here. So that's something interesting that we need to handle. So this is how we actually do it. We first add the lower bytes in the accumulators, just using our most common instruction for addition, which is ADDA. If you go to your instruction set, at the very first page, you will find this instruction ADDA, which actually adds the content of accumulator A and accumulator B, and then save the sum, meaning stored the sum into accumulator A. So we can use this instruction, okay, to add the lower bytes first, and once we add it, we save the lower bytes, meaning the sum of the lower bytes in our accumulator A. Now, for the next byte, meaning for the next higher byte, because in the next step you will be just dealing with the higher bytes, right, like 17 and C3. Now when you deal with those, instead of using ADDA, we use another instruction a little bit different than ADDA. We have it at the first page of the instruction set, which is ADCA. This instruction works a little bit different than ADDA. What is the difference? Difference is actually add A and the memory, right, meaning the data you give, but it also add the carry. So you see the carry, I marked it red, is also add the carry. That means whatever carry you had in the previous step, that is being added at the same time. Now this is really interesting. So to add the lower byte, we just use the regular addition. To add the higher byte, we use a different addition, which is ADCA. Now why is this? Because when you are adding the higher byte, it's possible that when you did the lower addition, you had a carry, and now you want to add the carry. Okay? Now remember, you will always actually have a carry, meaning even if you don't have a carry of 1, you might have a carry of 0. We know that we don't have to add the carry of 0, but no matter what carry you have, you always want to add it just to be in safe side. So you always use this ADCA instead of ADDA for the second byte and the higher bytes. Meaning, if you have a third byte, if you have a fourth byte, your number can be longer than even 2 bytes, right? So you will keep adding those higher bytes using ADCA instead of ADDA, because you always want to take care of the carry you had in the previous edition. You want to add that carry. So basically, if you add using ADCA, then when you are adding 1, 7 and C3, this one will be automatically added because your microprocessor knows that there was a carry in the last step. How microprocessor knows it? Because of the flag. Because remember, we talked about the flags, right? Remember, every time you have an addition and if you have a carry, your carry flag is set. Now, your microprocessor already knows that you had a carry in the last addition because of the flags. Okay? Because you are not saving the carry, right? You are just saving the answer, meaning the sum in the lower bytes. But your microprocessor will always know that you had a carry or not in the last addition because of the flags. Any question here? Okay, now our next question is, can we add long, meaning multiple bytes, BCD number in this manner? Now we now know that how to add the long numbers in hex, but the problem is, if you have BCD numbers, again, don't get confused by the word BCD, because just think the BCD numbers are decimal numbers. Okay? Now what happens if you have BCD numbers and you are trying to add the BCD numbers in the same manner? Now, the microprocessor, we use the family of microprocessor we have from the Motorola, they cannot add the decimal numbers. Okay? Now this is the problem. Now you are not converting your hex number into decimal, but how can you really add the BCD numbers which look like decimal numbers, but they are actually hex numbers? Okay? Now, first we need to know why this addition is not possible in 6800 by 6800 microprocessors. Now this is the reason why you cannot actually add. I mean, you can add, but you cannot get the BCD sum. This is the reason. The reason is, microprocessor can always add 2 numbers, but the problem is when you have a sum of more than 9, then you run into a trouble. Because think about the binary decimal addition. When you add 2 numbers and when you have more than 9, meaning like 10 or 11 or something, then you have a carry of 1, right, in the next column, meaning when you are doing the decimal addition. But when you are adding the hex addition, the problem is, if you have a sum of like 10, your sum is actually A, right? There is no carry, because A belongs to hex digit. That's actually the problem which you will run into. For an example, if you look at these additions here, all these additions are correct if you think these are hex addition. But all of these additions are incorrect if you think these are decimal addition. For an example, let's say you are adding 7 plus 5. Now if these are hex numbers, 7 and 5, answer is 0C, which is correct, right? Because C is 12. But if you think that, okay, I'm doing the decimal addition, the answer should be actually 12, right? But you don't see 12 here, it's actually 0C. And C even doesn't belong to decimal digit, right? Do you see the problem? Now for an example, in the next one, you are adding 15 plus 26, your answer is 3B. B even does not belong to hex. I'm saying the decimal digit, right? So that's not right. And here, you are adding, let's say, 39 plus 38 in hex, which is right, 71. But if you think these are decimal addition, your answer should be 77, right? Now this is the problem, because if you really try to add the 39 plus 38, just writing 39 and 38, your microprocessor will always give you the answer of 71. It will never tell this is 77, because microprocessor always treats your number as hex. Now how can we fix it? Again, we can always look at the number and we can manually always fix it, but we don't want to be manual, meaning you can have exceptions, and instead we use some rules to fix it. Meaning, if you really want to add these numbers as decimal number, we have some rules. And if you just follow the rules, you will always get the correct answer in decimal. Okay? That is called decimal adjust. Meaning the idea of correcting is called decimal adjust. And then for doing the decimal adjust, we have an instruction in our instruction set which is DAA. That's also in the first page because it's alphabetically ordered. And this is an inherent instruction. So it's just DAA. There is no operand. Okay? Now, how does it work? You might be wondering to see this is really like a magic. So for an example, remember in the last step, last slide we showed you that, okay, we are adding 7 and 5 as a decimal number and your answer should be 12, but you are getting 0C because your microprocessor is treating the number in hex. But surprisingly, if you just add 6 with any addition, any column like this, for an example, C is not the right digit you should get, right? Meaning if you're treating the number as decimal, just add 6, it actually fixes the sum. That's really something like a magic, because if you just add 6 here, it actually fixes it to 12, which is the right answer in decimal if you are adding 7 and 5. Right? You should get 12. Same is here. If you are adding 6 with column B, you should get 41 in decimal, which actually is the right sum when you are treating 15 and 26 as decimal number. Same is for the last one. Remember, if you are treating 39 and 38 as decimal, your sum should be 77, which also can be fixed just by adding 6. Okay. Now let's really see how the rules are applied. Now here are the rules that actually fixes any BCD sum. Okay. Now the idea is we have 2 rules, very simple rules. Now the rule number 1, we always add 6 to every illegal BCD digit. Now what do I mean by illegal digit? We actually treat A, B, C, D, E, and F as illegal digit in BCD. Why they are illegal? Because these are actually hex digit which do not belong to BCD numbers, right? Because we don't have any A in decimal numbers. We don't have any B in decimal numbers. We don't have any F in decimal numbers. So anytime in any column, if you have this weird, meaning any of these digit, you just add 6 to that column. That's rule number 1. Rule number 2, we add 6 also to every digit in the sum that had a carry of 1 to the next higher digit. We'll show you some examples, then you'll know exactly how to do it. We also want to make sure that decimal adjust only works for accumulator A. We don't have any decimal adjust for accumulator B. Okay? So anytime if you have to do the decimal adjust, you will be always using the accumulator A. Now remember, you actually don't have to apply these rules in your program, because all you have to do is you just have to say, okay, DAA, which is decimal adjust. Your instruction automatically fixes the addition by following these 2 rules. Okay? But in this class, we are just trying to understand how decimal adjust works. So that's why we are talking about the rules, and we will actually try to fix the sum just following these rules as an example. But in the real program, you actually don't have to do anything for these rules, because all you have to do is just write DAA for the decimal adjust, which will actually fix any decimal sum that you had in the accumulator A. We'll show you some example. Again, these are the examples. One more thing which you need to know, that decimal adjust does not work for subtraction or any hexadecimal arithmetic, because decimal adjust is actually designed to fix the hex addition, only the decimal addition, okay, like the BCD additions. Now, to understand it, we just give you some more additional example so you actually understand how things work here. For an example, in the left side, we are trying to add 93 and 25. Again, these are BCD numbers, okay? But you know that your computer will always treat, your microprocessor will always treat 93 as hex 93, 25 as hex 25. But these are let's say BCD numbers. And then let's say you are adding two numbers. What happens is your microprocessor will actually give you a sum of B8. But what is wrong here? If you think these are BCD numbers, B is an illegal digit, right? Yes. That's why I marked it red, because you cannot have B there. How do I fix it? Remember we said you actually have to add 6 with every column where you have an illegal digit. Now we have illegal digit B here, so we are adding 6 here. But we are not adding anything with 8, meaning we are just adding 0 though. 0 doesn't make any difference, but we are adding 0 with 8 because 8 is fine. So basically we are adding 6 0, which will actually fix the answer. So now if you see here, your sum is 118, right? Now this one is actually treated as a carry, which will actually raise your carry flag. But still, if you get this answer, your sum is correct, right? Meaning if you are adding 93 plus 25, your sum should be 118, right? Including the carry, which actually is the right answer if you think this is a decimal addition. Now another example, I have a little bit longer number than 1 byte. Now the first number that I have is 2969. The second number that I have is 8713. The same problem, this is a BCD number, but your computer will treat this as a hex. How do you fix it? So if I just use the microprocessor instruction like ADDA to adjust it, I'm saying to add it in two different, using the multi-precision addition, what happens is you will end up having some digit like this, B07C. Now, what are the illegal digits here? The B is an illegal digit for sure, right? C is an illegal digit which needs to fixed. But do you notice that I also marked 0 as red? Think about the 0. 0 is not an illegal digit, right? This also belongs to decimal. But why I marked 0 as red? Remember the rule number 2, we had actually 2 rules. The rule number 1 said every time if you have an illegal digit, you add 6 with that column. Okay? But we also add 6 to the column where you have a carry of 1 in the next column. For an example, if you look at this column carefully, you are adding 9 plus 7. So you actually have a carry which went to the next column, right? Do you see this blue one here? Now this one is a carry because of the previous column. Now every time for any column, if you have a carry in the next column, that column also needs to be fixed according to the rule number 1. So, I'm sorry, according to the rule number 2. So according to the rule number 2, you also add 6 to those columns as well. So basically, you have to add 6 to the column, this column, to this column also, and to the very last column. Because the 7 is fine, there is no problem with the 7. Because remember, no, we don't have any carry in the next column, right? It was actually 6 plus 1 and 7. We don't have the carry to the immediate next column, right? See, the carry we have actually is here, which generated because of this column, 9 plus 7, right? You actually got the carry because you are adding 9 and 7. But you didn't have any carry for this column because this column was like 6 plus 1. There is no carry for this. It's just 6 plus 1 and 7. I'm saying 6 plus 1 equals to 7. Oh yeah, 9 plus 3 is 12. You don't have any carry. This is just C, right? 9 plus 3 is 12. There is no carry. I'm saying this again, this is an hex addition. We are assuming this is a decimal addition, but in microprocessor is actually doing the hex addition. So 9 plus 3 is 12, which is C. There is no carry. Yeah, yeah. And then, but when you are doing 9 plus 7, that becomes 16. anytime you have more than 15, then you have a carry, right? So 9 plus 7 is 16, so you will have a carry. So and that's why you are adding 6. So now to fix this addition, you are actually adding 6 here, adding 6 here, adding 0 here, and adding 6 here. So remember, in the quiz, we will give you this addition and we will say, okay, now you know this addition, how to fix it, meaning what number you will be using to fix it. All you have to tell, oh, we'll be using 6606 to fix it, meaning you will add 6606 to fix it. Now once you add 6606, then you will have a carry at the end though, but including the carry, your answer is 11682, which is actually the right decimal sum. If you assume this was a decimal addition, that means this is a correct decimal sum of 2969 in decimal plus 8713 in decimal. Okay. Any question? If we understand up to this point, we'll also show you now how we actually do it in the code, because we need to see how we can fix it writing the instruction. Okay. Now here is what we are trying to do. We are actually trying to handle two different problems. In the first one, we'll add two numbers, and then we have to fix those numbers as binary sum, meaning the decimal sum. For an example, let's say we are adding 16 and 48 in decimal, and you know for sure that your microprocessor will not generate the right answer, because this will treat your numbers as hex, right? But this is what we're trying to do. We'll add these two numbers and we'll store the sum to a memory location 0040, because we always add the numbers and get the sum, and then once we fix the sum, we save it, we store it somewhere, right? So don't think that we always have to fix it into 0040. This is just a memory location. Randomly we just select it. That's something we are just saying, oh, I save it there, but you can save somewhere else. Sometimes it doesn't make any difference. Now, to understand how we actually handle this addition, remember, we know how to do the addition, but this time we are actually doing the addition in BCD. So that means we are actually trying to fix the answer. Okay. Now this is what we do. Now the first number that we have here is 16. So we load that number into accumulator A. Remember, we always work with A because decimal adjust can be done only in accumulator A, right? So don't forget that. So we load the first number, which is 16, in accumulator A, and then we load the second number, which is 48, into accumulator. We add that number to the 16, right? Because this will add 16 plus 48 and store the sum into A, because ADDA adds to number and save the sum into A. Now what is wrong here? The thing that is wrong here is, if you add 16 plus 48, here is the problem, because when you are adding 6 plus 8, your microprocessor will just add it as hex, right? So 8 plus 6 would be 14, which is E. But if you are thinking this is a decimal addition, there should be no E, right? 8 plus 6 is 14, so you know that there will be 4 and there will be a carry of 1. So you know that the answer is messed up, because your microprocessor is actually adding this as a hex number. How? No, this is a hex number. Don't forget, this is a hex number, but we are assuming this is decimal, because the binary coded decimal numbers are written in hex, but assume this is a decimal number. Now, this is what is a little bit tricky. Even if you see there is a dollar sign here, you know that this is a hex number, but you have to assume this is a decimal number, because binary coded decimal means you will be using the hex digit, but you are actually writing a decimal number. You know what I'm saying? So, for now, think that 16 is a decimal number, 48 is a decimal number. Okay? So, you are adding 16 plus 48, and you want to get the sum in decimal. Now remember, you have two rules, right, to fix it. We know how to apply the rule. We have seen the examples. But here, when you are writing the code, you actually don't have to apply the rules manually. Instead, what you do is, you know that you already had the sum. You already have the sum, right? After you have the line number 2, you already know that the sum is there. But you know that sum is not fixed because this is a hex sum. Now, if you really want to fix it, all you have to do is just write decimal adjust, DAA. Decimal adjust automatically fix the sum that you have in accumulator A. So that means it actually adds 6 with every single column which needs to be fixed. But you don't have to do anything in addition to writing this line, just one single inherent instruction. Now after this line DAA, you know that your sum is fixed. So all you have and sum is fixed and sum is stored into A. All you have to do is now just save that result, like the sum that you have in A, to a memory location, let's say 40. Remember in the original problem we said save the sum into 40, 0040. Now remember, the 40, you don't have to save it to 40. You can save it to anywhere else as long as you know where to save. 40 is just some memory location we just randomly selected. Okay, it doesn't have to be saved in 40. Now just by writing these 4 lines, you can always add the binary coded decimal numbers. Okay, now if you add this sum, what should be your answer? 64, right? Meaning, if you think these are decimal numbers, 16 plus 48 should be what? 64. Now once you save in 40, you will see the number is actually 64 because you already fixed that decimal adjust. But otherwise your sum would be 5E, right? If you think this is a hex addition, because after line number 2 it was 5E, but when you did decimal adjust, it became 64. It fixed it just by following the same rules that we saw in the last slide. Now let's extend the problem a little bit. Now let's say, so far we tried the binary coded decimal, we know how to do it, but what happens if you have the decimal number which are more than 1 byte long? In the last example we just added 16 plus 48. Now both 16 and 48 were 1 byte long, but right now we have 2 numbers. For example, see here we are just trying to add 4596 plus 4973. Now you can see that both numbers are 2 byte long in, right? 4576 and 4973, both numbers are 2 byte long, right? How do you add it?
Add first byte.
You actually add the lower byte first and then higher byte, right? So you actually will end up having 2 bytes in the answer, maybe a little bit more than 2 byte as well, because you might have a carry at the end. But if it is a 2 byte, you will be saving the lower byte into 0072. You will be saving the higher byte into 0071. Now these 71 and 72 memory locations we just selected randomly. I'm saying these just random memory locations. Let's see how we fix it. Now remember, in the first step we add the lower bytes, right? Now what is my lower byte for the first number? The lower byte is 96, right? What is the lower byte in the second number? 73. So if you see here, we are actually adding the lower byte for both numbers in the first 4 lines. Now how we got these 4 lines? Remember, these are the lines we always write to add the binary, I'm saying the binary coded decimal sum, right? Because we just add 96 plus 73, but we know that your microprocessor will generate the hex addition. To fix it, we do decimal adjust, right? And then and this is the lower byte, right? So we stored the answer. Once we fixed it, we stored the answer from A to 0072. That's my lower byte, right? That's my lower byte sum. Now once we are done with this time we handle the higher byte. Now what is my higher byte for the first number? 45, right? What is my higher byte for the second number? 49. Very simple. Once we add this, we do the decimal adjust, right? We do the decimal adjust, right? And then we stored the result into 71. That was meant, that was in the question, right? They just stored the higher byte into 71. But did you notice the difference? Look at the difference carefully. Did you notice this difference? Because when we added the first byte, meaning the lower byte, we used the instruction ADDA. But when we added the higher byte, we actually used ADCA. Do you remember why we do it? Because when we had an addition in the lower byte, you might had a carry, right? Remember, we talked about this at the first, right? Multi-precision addition. So what happened was, when you add the lower byte, I actually showed you here, what happened was you were adding 96 plus 73, your sum was 09, but you had a carry of 1. Now what happened is, when you did the decimal adjust, it actually fixed your sum, which makes it 69. Now remember, the 69 is the sum of 9. The 69 is not the right sum, right? Why 69 is actually 169. You know what I'm saying? If you're adding 96 and 73, your answer should be 169. But you try to accommodate in 69, I'm saying 1 byte, which is 69, but you had a carry of 1 here, right? Now what happened was, you stored 69 into 72, but when you were adding the higher byte, you used a different instruction for addition, so that the carry of 1 that was generated in the last addition is included here. You actually did not include the carry manually. All you did is just add it using this instruction. When you did that, this carry, which was generated in the last step, last byte, was included here, which automatically is taken care of. But again, you have a problem because you have an illegal byte here, right? I'm saying illegal digit, right? Then you fixed it by doing the decimal adjust, which made it 95. Now at the end, you save 95 into memory location 71. Now at the very end, you got the sum like 79569, right? That's the final sum, right? Because you have 69 in the lower byte position, you have 95 at the higher byte position. That means what? That means your final sum is 9569. Now if you add these two numbers, 4596 plus 4973 in decimal, your sum should be 9569. Try it in decimal addition. So you actually fixed it. Meaning you have taken care of two separate issues. Issue number one is you added the numbers and you adjusted using the decimal adjust. And the second issue was the number was longer than 1 byte. So you handled every byte separately, but when you did the lower byte, you had a carry, and which was taken care of when you did the higher bytes. And every time you do the higher byte, you always use the ADCA. Say it again.
Where did you get the 60 from?
Why did it get 60?
Yeah.
How do you fix the decimal adjust? Remember, you add 6 with the columns which are illegal. So if you look at this one, there are two rules, right? Rule number 1, you add 6 with every column which are illegal. Rule number 2 is you add 6 with every column which had a carry, right? Now here you got this 6 because you have a carry in this column, right?
Yeah.
So you actually add 6 here. Same is here, you got 06 here because look at this. This is the illegal digit, right?
Right.
F. So that's why you add 6 there. But you did not add anything with 8, so that was 0 because there is no problem with that column.
Correct.
So I actually added 60 in the first column, the first decimal adjust. I added 06 in the second decimal adjust because I was just following the rules. Now if you recall, this is actually the rule number 2 and this is rule number 1, right? Now again, don't forget, you actually don't have to add 60 and 06 manually because all you are doing in the code is you are just writing DAA, which actually is fixing that. But we want to make sure we understand how the decimal adjust is done. That's why we learn the rule and we know that, okay, in the first one you are adding 60, in the second one you are adding 06, but you are not actually doing it manually. All you are doing is just writing DAA, and DAA automatically applies the rule, whatever is needed to fix it, right? In the first step you need like 60 to fix it, in the second byte you need 06 to fix it, which was automatically applied by DAA. Any question? Okay, now let's try to see how the lab 2 is designed. It's pretty much the same thing. In the lab 2, we are trying to add two numbers. Each numbers are 3 byte long. We know how to do the 2 byte. 3 byte is pretty similar because the higher bytes are pretty same. Now you have two numbers. Each number is 3 byte long. We do the number like this. For an example, let's say the first number that we have is like this. This is my first number. I actually save the numbers as using some variables. Remember in the C++ class you use variables, right? We can pretty much do the same here like this. Let's say the first number is actually 249645. How did I save it? I actually saved 24 as A1. So every time I write A1, that is treated like 24, which is the higher byte of the first number. Then I save 96 as A2. Then I store 45 as A3. So basically A1, A2, A3, these are like variables. I'm saying to make it simple, think it just like C++ variables. Like whenever you are writing A1, your microprocessor, your program knows that you are actually writing 24. You see what I'm saying? When you are writing A2, your computer knows you are writing 96. When you are writing A3, your program knows you are writing 45. Okay, now my first number is 249645. My second number is actually 157386. So similarly, I save the second number as B1, B2, B3. Because again, why did I use 3 bytes? Because I know that I cannot save more than 1 byte at a time, right? So that's why I did, right? I just know that the number is like 3 bytes long, so I did that. And I reserved, now I can also reserve some memory location. So what I did is, I reserved some memory location where I'll be storing the result. Now this RMB means reserve memory byte. Now this actually saves 1 byte for S1, 1 byte for S2, 1 byte for S3. Again, treat this S1, S2, S3 as variables. When you will have your answer ready, meaning the sum, final sum, we'll save the higher byte in S1, middle byte in S2, lower byte in S3. But right now, we're just reserving the byte because you can always reserve the byte in the low-level language like this. This one means how many bytes you are reserving. So you are actually reserving 1 byte for S1, you are reserving 1 byte for S2, you are reserving 1 byte for S3. You can reserve more than 1 byte, but right now we don't need it. We just need 1 byte. That's why we reserve 1 byte. Now, as you see, this is exactly what we are doing. We are actually trying to treat these numbers as decimal number. So we have the first number, which is 249645, the second number 157386. We are just trying to add those two numbers. But if we treat these numbers as BCD, our BCD sum should be 407031. This is the BCD sum, meaning the decimal sum, okay? So this is exactly what we are expecting. So our first two numbers, we know that these are given, but after we are done with this program, the program will actually generate the sum of 407031. That's a decimal addition, right? Now, to understand the program, we actually don't want you to start from the scratch. So what we did is, we actually have written some lines here, but we did not complete the program. All you have to do is complete it. We give you a couple of lines, but you have to fill some more lines, okay? Now this is what we did. Before we start the program, notice that every single line that you are writing, you actually have to start with a preceding tab, because you have to give a tab and then write the instruction. We have a reason for it. We will explore it later, okay? So every instruction you write, make sure you put a tab. Now these lines are already given to you, but you have to fill some of the lines. So at the first line, you said org D000. That actually tells your microprocessor that, okay, start my program from this location. You know that your memory location starts from 0000, right? But you don't save the program from 0000 because at the very first locations, you have a plenty of pre-saved data. We'll talk about this later, okay? So that's why we actually start the program from D000 most of the time. Then you initiate the stack. We'll talk about the stack later as well. But this is exactly what we are doing. Look at this. We are adding the lower bytes. Do you notice here? What we are adding? We are adding A3 and B3, right? If you go back, look at the number. A3 is the lower byte of the first number, right? Which is 45. And the B3 is the lower byte of the lowest byte of the second number, which is 86. So at the very first step, because you always start from the lowest one, right? You first add the lower byte, and then you will add the middle byte, and then you will add the higher byte in 3 steps. So we are actually adding the lower byte here, and then we are doing the decimal adjust, right? We always have to do the decimal adjust, and then we are storing the sum in S3. Remember, you have 3 bytes to save the answer: S1, S2, and S3. We actually save the lower byte in S3, middle byte in S2, higher byte in S1. So we save the lower byte in S3. Then we are done with the lower bytes, lower byte, right? Now let's handle the middle byte. How we do the middle byte? We do what? We add A2 and we add B2, right? A2 and B2 are the middle bytes, right? Because A2 means, if I go back, 96, right? And B2 means 73. So we are actually adding 96 and 73 middle byte. But do you notice the difference? This time we are adding a different instruction for addition, which is ADCA. Why is that? Because we want to take care of the carry if we had any in the previous column, right? Starting from the second byte, we always do it, right? So once you do it, you actually have to do the decimal adjust and store the result, and then later on you have to do 4 lines. Every time you write 4 lines, right? You write 4 lines for the lower byte, you write another 4 lines for the middle byte, you write another 4 lines for the higher byte. We actually did not write the 6 lines in the middle because we just wrote 2 lines for the middle byte. So you have to add another 2 lines for the middle byte, and you have to write 4 lines for the higher byte. So you actually have to fill this gap, and then you are done for this program. Okay? So once we finish the program, our result will be stored in S1, S2, and S3, right? Those are some memory locations. So that means you will actually not see the result, because what happens is after you are done with the program, your result is actually saved into memory location. But there is an instruction which you can type in your terminal, which shows the memory map. The memory map. Remember the memory map that you see in the quiz section? The same memory map you can see also in your compiler. How you can see it? We use an instruction that is called memory dump, MD. Just writing MD and then writing to address, you can actually see it, because when you write to address, what happens is your microprocessor actually show all the bytes that you have between these 2 addresses. Now let's say I wrote some address in address 1, I wrote some address in address 2. Okay? Now for an example, just to understand, let's say the first address that I wrote is 0015, and the second address that I wrote is 00B9.
It's random, right?
So no, I just selected 2 address. Okay? Now that means you actually want to see the address location 0015 to 00B9. Okay? But this is the tricky part. Your microprocessor will actually start from 0010. Why? Because it actually always starts from the beginning of the row. Remember, if you recall the memory map, it starts from where? 0010, and the next row starts from 0020, the next row starts from 0030, right? The next row starts from 0040. So Even if you said, okay, show me from 0015, it will actually show you from 0010. Do you see the catches? So even if you are writing 0015, it will actually start from 0010 because that is the beginning of the row. Okay, and then you said, okay, show me up to 005 00B9, but your microprocessor will complete the whole row where the row ends. The first row ends at 1F, right? Second row ends at 2F, then 3F, 4F. Those are the ending location of the row, right? So even if you said, okay, show me up to B9, your compiler will show you all the way up to BF. You see what I'm saying? So remember this, okay? Even if you mention some address, it will actually show you all those addresses, but it will always start from the beginning of the row to all the way to the end of the last row, okay? So this is what I'm just trying to show you, okay? Let's say in the instruction you said, show me from 0015. Now this is your 0015 location, right? But your microprocessor will actually show you from here because that is the beginning of the row. You see what I'm saying? It cannot start from the middle of the row. It will always start from the beginning of that row, okay? And you said, okay, show me up to B9, which is here, right? Which is 6C, I'm saying B9, but it will actually complete the row all the way up to this point. Because it cannot break the row. It cannot start from the middle of the row, and it cannot end at the middle of the row. It will actually complete the whole rows. So even if you said, okay, show me from 00B9, I'm saying 15 to 00B9, it will actually show you from 0010 to 00BF. This whole bunch of locations. Then you can read or see what exactly you need to see from different locations. We'll be exactly doing the similar thing here so that we can see the result, because after we are done with the lab 2, you will not see anything in the terminal window because you know that something is changed in the map. So you want to see the map to check whether your answer is saved correctly, meaning your program you did correctly. Okay. Now to understand this lab, we actually try some pre-lab quizzes. Okay. In the pre-lab quizzes, we pretty much do the same things that you have seen here, meaning how to do the multi-precision addition, how to fix the decimal adjust, right? And how to save the answer, how to write those 4 lines for every byte. Remember, the 4 lines are different because when you do the lower byte, you do an addition instruction, but when you are doing the higher bytes, you do a different instruction, right, for addition. So we try to understand all those instructions, how to modify the program for lab 2. So to understand it, we'll try all the pre-lab quizzes. We have actually more than one. I broke it into multiple pre-labs so that we don't have too many questions in each of those. So we want to finish all of those with at least 80% so that we can start the lab. So I'll give you the procedure for lab 2, but before we start the lab, we want to make sure that we finish all the procedure. I'm saying all the pre-labs with 80%. There are probably 3 pre-labs. I'm saying 3 or I'm sorry. There is probably actually 1 or 2 pre-labs, but it's all the questions that you will see in the pre-lab belongs to this slide. Okay, so you'll pretty much get all the answer here, but you have to look at and find it and understand everything that we have here. Let's go to the quiz section and let's try the pre-lab for lab 2 so that we can work on our lab 2. Meanwhile, I'll give you the procedure for lab 2. Okay, let me stop the presentation here, and I'm sure that you probably will have questions when we'll be doing the pre-lab quizzes, and we'll answer those questions accordingly. Okay.